In this video, we're going to talk about prime numbers. And we'll start off with this quote from Euclid. Prime numbers are more than any assigned multitude of prime numbers. Well, that was his way of saying basically for any fixed natural number, say, there are more prime numbers than that natural number. And the way we would say it is, if that's true for all natural numbers, we would just say there exists an infinite number of prime numbers. The ancient Greeks had a vision of infinity that was different than ours. It's basically described as lines, like the x-axis or the y-axis. Lines are line segments that can be extended indefinitely, but they wouldn't consider those lines as being infinite length. So, we are going to prove this theorem. There exists an infinite number of prime numbers. And we're going to use a proof by contradiction. So I'm going to start off by saying, to the contrary, suppose there are only a finite number of prime numbers. Suppose there exist only a finite number of prime numbers. Well, if there are a finite number, then we could name them. Namely, and what I'm going to do is I'm going to call them P1, less than P2, less than P3, less than, all the way up to, say, PR. So P1 through PR will be our entire list of prime numbers, and they're written in increasing order. So we already know what the first prime numbers are. That would force P1 to be the number 2. That's the first prime number. P2 would have to be the number 3, and so on. Now, let's define a new number. Let's let capital P be the product of all those primes plus 1. All right, now note, you might be thinking, oh, that's another prime number. Well, no, it's not that easy. If that were the case, that would change the world. But if you think of, take two prime numbers like 3 and 7. You multiply 3 and 7, and then you add 1, you get 22. That's not a prime number. But let's consider this P, which is P1, the product of P1 through PR, plus 1. And let's let the number Q be a prime number such that, I'm going to put ST for such that, Q divides P. All right, so P is some number, and we want Q to be a number such that Q divides P, that goes into it. Okay, so I mean, if P happened to be prime, then Q would equal P in that case. All right, so notice though that Q cannot equal any of the PIs, I'll just list them out, P1, P2, all the way up to PR. Why not? As otherwise, we have Q dividing big P and Q dividing P1, P2, all the way up to PR. And let's see why we know that. Well, we know Q divides P. And if Q is equal to one of these, then certainly if it were equal to P1 or any one of these, it's certainly going to divide into this product of numbers, since Q would be equal to one of those numbers. And what would that tell us? Well, that would tell us also that Q divides P minus P1, P2 to PR. This has been a little while since we've seen this. And this would give us a contradiction, because this is equal to 1, right? Because P is all of this plus 1. So if we take P minus this, we get exactly 1. If Q divides 1, that means Q is equal to 1, so Q would not be a prime number. So we certainly reach a contradiction, but why do we reach the contradiction? Or, in other words, how can I make this statement? This came by number theory fact number 6, which basically says that if A, if A divides B and A divides C, we know that A divides B minus C. The actual fact said that if A divides B and A divides C, then it divides any linear combination of B and C as well. So this would be 1 times B and negative 1 times C. Okay, so that would be impossible. Thus, Q is a prime number not in the list. P1, P2, all the way up to PR. That gives us a contradiction, because P1 through PR was supposed to be all of the prime numbers. Well, we found out that another one exists, so that contradiction, therefore, there are an infinite number of prime numbers. Infinite number of prime numbers. And that's the end of the proof. And this proof always shows up on an exam. The proof of there exists an infinite number of prime numbers. Now, since we're talking about prime numbers, I'm going to state a problem. It's an open problem. That's the end of that proof. So open problem says, let P1 less than P2 less than P3 less than, and so on, be a sequence of prime numbers. Find a function f such that P sub k, one of these, is f of all of the previous ones. Pk minus 1, Pk minus 2, all the way down to P1 for all k in the natural numbers. So this does not say that this has to be every single prime number, but just an infinite list of them here. We want to find a function such that any one of them, pk, could be found by plugging all of the previous prime numbers into this function, and it spits this one out. Which would then mean we could get pk plus 1 by plugging pk also into here. So we essentially would find a formula to get not absolutely the next prime, but a next prime, a subsequent prime number. This is an open problem, and it would probably be an instant PhD degree for you if you could ever solve that. So an interesting number theory open problem.